All right, welcome to Pump Theory for 2021. The This session will cover both pump theory and kind of tie that back into that whole hydraulic theory and how it all goes together. We'll dive more into the hydraulic theory piece as we go through the hydraulics. You may get exposure to that before and after this session, but it'll be there, and this will be the piece that kind of fills the gaps in between, so to speak. In the current circumstances, we're looking to manage for COVID exposure, and we're looking to do some stuff virtually, especially classroom type, lecture sessions that aren't super interactive, albeit there's opportunity to interact when we do this in person. Um, we found that most of what we pulled out here it's not that interactive. It's information, and there will be opportunity to follow up with questions both in a virtual classroom environment where we're actually there, and also in a direct classroom environment when we're talking hydraulics type stuff. Some follow up in person to make sure everybody's on the right page. So, by us addressing some of these units, like this one virtually, in different formats, it builds more time class for hands-on sessions, which everybody likes to go do what they've learned. And rather than cram a whole bunch of stuff into a short amount of time, it gives us more opportunity to take our time, do a better job of teaching it in person. This collection of materials will also remain available to you in the future. If you ever need a refresher or reference, you'll be able to grab a hold of this and take a look at it. There's going to be several short videos. There's a lot of information in this pump theory piece. We've kind of broken into a whole bunch of short videos, and some of that stuff's very specific to the academy, and some of that stuff's more specific to like a PMS 419 engine operator class. But we need to cover both of those, and doing it in this format allows us to get a whole bunch of that information out to you and not cram it into a super short in-person lecture session where we don't have a lot of time. So this way you can peruse it on your own ahead of time, on your time and schedule as you can make work. These videos will be organized in playlist in order, and will provide student material for note taking and tracking all of that in this presentation. Hopefully that keeps you from getting overloaded by a whole ton of information in a 2-hour long PowerPoint lecture, and instead we can look at it in 10-15 minutes chunks that you can work through and then work on to the next one. So why do we study hydraulic theory, or pump theory for that matter? The points up there are valid, to determine pressure needs. Sure, that's very much the hydraulic theory piece, and that really ties into what equipment do I have that can do the job I'm asking of it. I think that's really critical, and that's where that number crunching little math piece kind of ties into. It's about capabilities and whether or not I can pump that hose lay. It also helps me troubleshoot other ways, other supply options to get water to the hose lay that I'm trying to pump. But really, that underlying theory piece, it's a tool to make you better, if not the best resource out there, and getting you to understand how to get the most out of your equipment and your system, and that keeps you fighting fire. Okay, objectives. Not entirely all inclusive here. There's probably a few more things that we're going to cover, but we will talk about the factors of the hydraulic formula. We'll touch on a little bit of the why in here. We'll also look at how we move water in our pump systems. Look at the capabilities of different equipment, also the limitations of different equipment. troubleshoot some problems, recognize relationships between hose life factors. I think that's probably the most important piece there, is recognizing those relationships. It's a little bit of physics, a little bit of math and science, how it all goes together to either work or not work, and then how you come up with solutions. Why does this pump theory piece matter? The idea is to take a minute to make a good plan. You can pump anything. It can be done. It may not be feasible in the sense that it's just going to be too hard to do or too labor intensive to make it worthwhile, but it can be done. And there's always several ways to approach any given problem. I get all kinds of random phone calls at all kinds of random hours about, hey, so I'm out here on this fire and we're trying to do this. And we talk about it for a while. We usually come up with some sort of a solution for them to try. The idea here is collect the information and know what you're trying to do. So you need to have an objective. What are you attempting to accomplish? I want to get water from here to here. To do what with? To spray out of a nozzle or to fill an engine? Those kinds of functions are important. You got to have that objective. So lock down that objective, design your system, the overall system, to meet all of your needs. You can do more than one thing. In this example here, not only are they pumping hose lays up and down this division, but they're also storing water up and down the division that they can use. So they have supply and they have supply storage. This example in the picture here, there's 232 sticks of 1.5-inch hose. And it's a real division on a real fire that someone was trying to pump water on. There's 5 pump stations, there's storage built in, there's supply for that storage, and nozzles being fed all at the same time. Okay, there's a lot going on here. It requires a clear plan, and you have to get 5 pump operators working together to facilitate the outcome. So, taking a minute to make a really good plan when you're dealing with this much complexity is a really good idea. And ultimately, we want you don't have to come out of this being the expert. We want you to be able to function with that expert at the very least to help them come up with these kind of solutions. All right, so we'll start getting into some of the things that affect us here. Atmospheric pressure. No, we're not talking weather. This is not a 290 review. We're talking about drafting. We're talking about how our pump can pull water and how this works. Air pressure plays a role because it has weight. Think of yourself sitting in a giant pool of air. Just so happens you can breathe that giant pool of air. But that pool of air has more pressure at the bottom because there's more weight of air sitting on top of you. Specifically, that's 14.7 psi if you're at sea level. So we're remembering that air pressure plays a role here. If I look at how this works, grab my little pen thing here. I have a pump right here in the middle of this truck. And that pump is spinning and trying to push water because pumps don't suck, right? So my pump's pushing water, and on the suction side, I know pumps don't suck, but we still use the term all the time. On the suction side of that pump, it's creating low pressure, creating an area of low pressure. Well, my atmospheric pressure out here, ooh, my arrow wasn't very good, but you get the idea, is pushing down on my water source. And I have 14.7 psi at sea level of pressure pushing down on my water source. And it pushes on that water source, and because I'm creating low pressure in my pump, it starts to push the water up my draft hose. Okay? So as long as I can get primed my centrifugal pump, and we'll get into that part here in a little bit, my pump pulls water up as the atmospheric pressure is pushing down on my water source and pushing it up my draft hose. That's how the draft works. So with that, we have some capabilities and or limitations. I guess really this is as much a limitation as a capability. Max theoretical draft is 33 point irrelevant. You can't ever attain max theoretical, so it's just a cool number that's out there. But there we go. Max attainable at sea level is 22.5 feet. There's a number that actually means something to me. If I'm trying to pump water and the surface of the water source is 22.5 feet below me, that is the most I'm going to be able to do, assuming I'm at sea level. We keep referencing sea level. We reference sea level because it's a given point where that atmospheric pressure is basically at its highest. The lower you are in elevation, the more air you have stacked on top of you, and therefore atmospheric pressure is higher. If you were at a place below sea level, you would have more atmospheric pressure. The rule of thumb here still applies, even if you were going downhill, but that's not really what we tend to do. Typically, we go up in elevation, and you will lose 1 foot of draft ability per 1,000 feet of elevation gain. Yeah, that can be not too big of a deal, but it can end up being significant. Generally, we do a really good job of getting really close to our water sources, but if I'm drafting off a bridge or something like that, where I do have quite a bit of elevation change, that is something to pay attention to. So I'm here at 3,000 feet. You could be wherever you are. And if I'm here at 3,000 feet, I'm losing 3 feet of draft capacity. So I can only pull water straight up 19.5 feet. Now that's not the length of draft hose. That's just elevation change between the eye of my pump and the surface of the water source. 19.5 feet is the max that I can do here at 3,000 feet. That's assuming I have a really good pump. Everything is working well. All my components are nicely tight and fitted together and not leaking air somewhere along the way. Okay, now we're just restating what we've done already, using a little different terminology, because this is common terminology that's thrown out in this pump theory type of piece. Hg is mercury. So 1 inch of mercury lets water 1 foot. Inches of mercury is a measure of vacuum. You can also commonly hear it stated that 1 inch of vacuum lifts water 1 foot. And technically 1 inch of mercury or 1 inch of vacuum lifts water more like 1.14 feet. We round that. Okay, so officially we say we round that down to 1 foot for margin of safety. That's one way to look at it. It's a lot easier to calculate when you just say 1 to 1. And we're estimating here anyway. We estimate our elevations. I've never seen an engine guy pull out his tape measure and measure that distance. I actually did do it once just to figure out what was wrong with the pump. But generally, you're not taping off that distance, you're estimating it. Our systems aren't perfect. Nothing in our system is. I may have a pinhole in a draft hose that I can totally perform right through and never notice the problem. Maybe my pump's not working at its maximum capacity anymore because it's old. Any of these things could happen. We round things so that we calculate our estimate. Are we precise? No, we're not precise. Are we accurate? Yes. 1 inch to 1 foot as far as vacuum goes and as far as lifting water goes, that's a perfectly good calculated estimate. So here we are. We've already covered this for the most part. I lose an inch of vacuum, or really I lose that 1 foot of draft capability. for every 1,000 feet above sea level. I also lose that 1 inch of vacuum capability in my pump for every 1,000 feet above sea level. It's the same thing. It's not, they don't compound here. It's the same effect producing two different definitions of the same thing. So every time I go up 1,000 feet, I lose 1 inch of vacuum capability and 1 foot of draft capability, but not both. It's just a different way to describe the same effect. And that kind of explains why, the atmosphere is thinner, it's less dense. There's just not as much weight sitting on top of that water source. The textbook here says for our purposes, water is considered non-compressible. The reality is that water is really not very compressible. 300,000 psi is required to compress water by 1%. Okay, we can't deal with those kinds of pressures. We don't have any equipment that does that. So yeah, it's not compressible. Here, and really what we're getting at is, even though water's elastic and fluid, it's finite in size. So 1 pound of water is almost always the same size. So since water is not compressible, it has a constant volume. That can be useful to us. There we go. It's good to know how much water is going to be in your hose. 100 feet, 1.5 inches is going to be 9 gallons. 100 feet of 1 inch is going to be 4 gallons. Those are useful numbers in calculating how much water it takes to fill up a hose lay, let alone to feed it afterwards. I also really like this number. 1 cubic foot of water is 7.48 gallons. That comes in pretty handy for me when I calculate how big a water source is, right? You can do a little bit of simple high school geometry and figure out the volume of a container that happens to be full of water in this case. So there you go. That's your 3.14 or pi times the square of your radius times your height, this cubic volume. Multiply that by 7.48 gallons, and you get gallonage. Looking at a square container, it's just length times height times width in feet gives you volume in cubic feet, and you multiply that by 7.48. It's nice to know how much volume you have available to you. It's also nice to be able to label that and make a sign about your referencing your water source. So this guy over here is building signs so that we can actually know how much water is in that tank. If you've ever had to drag around an 1.5 inch hose full of water, you already know this. It's heavy. Okay, it's pertinent for engines when they have full tanks of water. Not that it should change the way you do business in general, but it's good to know. That stuff's heavy. Okay, maximum efficient flow rates. So this isn't, perfect science at this point. This is a piece that is useful information, however. Think of it this way. 1.5 inch hose is what I'm going to use as an example. And it says the maximum efficient water capacity of 1.5 inch hose is 100 gallons a minute. Basically, I can't really flow any more than 100 gallons a minute through an 1.5 inch hose, at least not very far. I've done it. I've pumped 150. I've pumped almost 200 gallons a minute through an 1.5 inch hose, but it was through a 50-foot section during a pump test. It wasn't in a hose lay. So if I'm looking at, any kind of significant distance, which is just a few hundred feet to get to significant distance, these are the numbers that I'm kind of using. 3/4 inch hose really isn't going to move more than about 13 gallons a minute, give or take a little bit. Really high performance pump might be able to cram a little more in there, but generally It's about all you're going to get. 1 inch hose is 30 gallons a minute. So you're not going to put a 60 gallon a minute on the nozzle on the end of a 1 inch hose and actually expect to get 60 gallons a minute out of it. That's really the point. And when I get down to that 100 gallons a minute, an inch hose or inch and a half hose, if your hose lay is demanding more than 100 gallons a minute, you know, the number that comes up most often in our exercise is something like right around 105. You might be able to get that to go through there because that's not much more. But boy, at 120, that's probably ain't going to go. Probably not going to work. You're going to need to design a system that's capable of handling and flowing more than 100 gallons a minute. Parallel hose lays can do that because they're splitting the volume. And when I'm looking at 1 3/4, I think it's impressive that by going up 1/4 of an inch, I'm going up 120 gallons a minute for capacity. If you really need to go long distances, 1 3/4 is a great way to go. But it's not like we have that laying around. And then 2.5 being capped at about 300 gallons a minute, I think that's pertinent because if I'm running some of our big type 3s and I'm plugged into a hydrant and that boosts my performance a little bit, and I'm moving 300 gallons a minute. I have seen it where I've collapsed a soft suction line because we were moving more than 300 gallons a minute out the discharge deck gun of a Type 3 engine. So recognize those limitations. This is a pretty handy little bit of info right here. All right, NFPA hose test standards. It's an interesting little piece that I think we mentioned it in the pre-work that there are hose test standards. Generally, our hose is tested to 300 PSI for 3 minutes. The other piece of that is you can only test 3 lengths of hose at a time. Well, actually, according to the Water Handling Equipment Guide, and you can read all about hose test standards on page 125 or starting on page 125 of the Water Handling Equipment Guide, it says it's just limited to your location. And generally, we don't have a lot of places that you can do straight hose lays of more than 300 feet. But if you could put 500 feet out there, you can test all 5 pieces. It's not regulated to 3 lengths of hose any longer. And even NFPA has changed that. And from a hydraulic theory standpoint, the pressure is equal in all directions. Why would we have to limit it? I don't know why they did in the beginning or why they used to have a limit on that. But I think an important piece here is generally our hose is rated at 300 PSI. So if you're looking at a hose lay that needs 450 PSI to pump it, you may be outside of tolerance. It may not work. All right, improving drafting. So the easier you make it to draft, the more capacity your pump has to deliver on the other end, right? If you make it easy for it to pull the water in, then it's going to be able to push more out for you. So the easiest you can make it for a pump would be to actually pump water into it, like off a hydrant, off of another pump. That's going to massively increase its capacity for output. Considering that's not usually what we do, things to do to make it easier to draft or pull water, that's really what drafting is, pulling water out of a source into your pump and push it on out to your fire or your tank, is to get your pump as close as possible to the water source. If at all possible, get it below the surface of the source. That doesn't really happen very often. Not in an engine, maybe in a portable pump, but you get the idea. Increase the size of that suction. The bigger the hose you have, the more volume it can handle and move, and the less friction loss it's going to have. And you will have friction loss on suction. So make it easy. Get big. Use big suction. Use appropriate suction for your engine. I guess that's probably the better way to put that. You know, on a Type 3, you should really be using 2.5 inch suction. On a Type 6, you should be using 2 inch, not 1.5 inches. If you're using 1.5 inch suction, are not helping your pump out whatsoever. Same with the Type 4, 2-inch suction. That's the appropriate size. Okay, so the general rundown is right out of the ENOP course of how to draft using your pump, using your engine pump. And remember, when they reference draft here, don't remember, it's just when they're referencing draft here, they're really talking about drafting and pumping back into my tank. And really drafting, I draft every time I pump. I can draft out of my tank or I can draft out of my source. Either one of those is still pulling water and therefore drafting. In this case, we're talking about pumping water and drafting it from a source and pumping it into my tank. So locate water source with adequate supply. Great. Always obtain permission from the landowner before using a private water source. That's policy. It's debatable. I'll touch on it again later. It could be argued that you don't have to do that in some locations, but generally it's a lot better than staring down the barrel of a shotgun. So I like to ask. Your source site should allow for good egress and ingress. And if you don't have that, maybe you should develop it. Example on a fire, we set up a big tender fill site with an overhead fill that pumped out of a river. And it was a little too tight, too many trees. So we cut a couple trees down and made for better ingress. It helps. Plan accordingly, depends on your circumstances. Okay, your source site, your water source site, should be free of floating debris. Try and pump clean water. The cleaner the better. Try not to get junk in there. But boy, we sometimes have to just pump whatever we can find. Okay, all fittings and hoses on the suction side should be free of air leaks. It's only 2.5 in a Type 3, or some of the older Type 6s. It's not 2.5 anymore. It's probably 2-inch. That'd be more appropriate for it. But make sure you're actually using the wrenches and you're tightening down your suction. That's what's key there. The foot valve should be completely submerged, free of debris, properly functioning. We'll look at a little more of that when we talk about water sources and some creative ways to get water. Creative ways to keep your suction a little bit more cleanly functioning. Obtain a prime by using the hand or electric primer on the engine. Fill the draft hose with water manually. Set the water pressure shutdown switch to the upper override position. Leave the switch in position for the entire drafting process. You do not need to go into safety mode when you're drafting. You should be standing there watching it fill your tank, given the scenario that we're talking about here. The newer engines have a bit of an automatic override, which is pretty cool. And so get to know that as well. Sometimes they'll start without the safety on and you might confuse you. It certainly confused me the first time I saw it. Okay, number 9, set correct valve configuration. In the valves piece, we talked about this a little bit, but I'm going to just kind of sidebar here for a second. My methodology for pumping with an engine, it's a little more simplistic, or maybe not, but the first thing I want to do is figure out what source I'm pumping from. It could be a source outside of the truck, or it could be the tank. Those are my two options, and I open the valves accordingly. Hook up my draft hose, get a prime, make sure that I'm actually building some pressure with my pump, and then I can send it to whatever discharge I want. That can be back to the tank, or that can be out to a fire. But if you look at it from that standpoint, more of a 3 or 4 step piece, where's it coming from? Get it primed, build pressure, send it to wherever you want it to go. If you look at it that way, it commonly works out a little easier. You're not thinking ahead of what valves to pull here or there, do this or that, just one step at a time. And you confirm that your pump is drafting water into the tank or pumping water into the tank, either visually by looking at the gauge or by looking at the tank. Okay. Okay, pressure and volume. So we're not really talking like the difference between a pressure pump and a volume pump. What we're looking at is my pump produces both volume, it moves water, and it produces pressure because I've constrained that flow of volume. Generally, we have centrifugal pumps, and we'll get into that here in a little bit, what exactly that means. But when we're using a centrifugal pump, that kind of caps me out in a balance of volume to pressure. And that's where those pump performance charts come into play. I can only do at my maximum RPM, I can only give so much volume and so much pressure. And if I have more volume demand in the system, I'm going to be able to produce less pressure. If I need to have more pressure, I'm going to have to produce less volume out the discharges. That's not necessarily out the discharge of the pump. Actually, it is out the discharge of the pump. Into the hoseway and out the nozzles. You might have to shut down more nozzles to give you more pressure. These things are inverse and they're very closely tied together. They're not entirely and exactly inverse, but they're mostly inverse once you're into a pumping operation. When I turn my RPMs up, so like there it says, if pressure is increased, then volume will decrease. Really what we're getting at there is in my hose lay, if there's an increase for pressure demand, then there will be a decrease in volume capability of my pump. The pump can't produce more pressure and more volume once I hit maximum, pump performance. Now, I can turn my RPM up and it's going to throw more water and therefore produce more pressure up to my maximum RPM. So really when I'm talking about pump capability, it's at max RPM. That's why portable pumps like Mark IIIs are really good examples of it, because they're the one pump that we all run at max RPM because that's what it likes to run at. When I'm looking at a $200,000 fire engine, it makes me a little nervous to crank that thing up as high as it'll go. I'm not always at max RPM. Just a couple different ways to look at that. So this really comes back to the performance curve on your fire engine pump. And another thing to keep in mind is that you can only flow so much water through a hose of any given size, as we looked at just a little bit ago. Gizmos. Gizmos are a fun little tool. There aren't a ton of them around. They're in places where big elevation is a significant factor. Big elevation and big hose lays are a significant factor, and people are more apt to have them. They restrict that water flow on big downhill hose lays to deal with those head pressures as you have them running down. So you can do it with a Y, just cracked appropriately. It's a lot less precise, but it does do the trick, and we all have them. It takes some practice to make that work. So take care of your pump. If at all possible, pump clean water. I mean, when you run dirt and stuff in there, you get scouring, you get wear on your equipment. Clean your strainer, because a clogged strainer makes your pump work harder. It's harder for it to pull the water in. Don't run the pump dry, ever. There's a little bit of tolerance there. And I think saying don't run it dry ever, I mean, it's true. You don't want to run your pumps dry. But at the same time, if I'm getting water up to it and it's turning, that's not necessarily, there's a balance. The key is that you can get them hot. And if they get hot, you can start breaking things like mechanical pump seals. So however you need to do it to take care of your mechanical pump seals and the equipment in there, if that means make sure that there's water sitting in it when you fire it up, great. because water absorbs a lot of energy or a lot of heat or heat energy. Minimize cavitation, so recirculate cool water into the pump. Yeah, that's why we have a bypass on every engine anymore. Monitor flow of water into and out of the pump. That's really, don't exceed your ability to get water in is the key. That's really what's going to cause cavitation, is you're pushing more than you're getting out. And we'll go into cavitation and what it means and what it looks like here in a bit. Don't redline your pump. Pumps are completely designed to run at their maximum RPM, and there's nothing wrong with that. You just need to make sure you're taking care of the power plant that's running that when you're doing it. You're running those little 3-cylinder diesel motors at, 3,000 RPMs. You're going to want to ease them back down and let them cool off before you just shut it down. Otherwise, your pump can push a lot of water. It can make a lot of pressure. You got to balance these pieces.